When you hear pi in math, you probably think of the Greek letter pi that equals 3.1419265358979323462 yada yada yada. I should probably stop there, because today we won't talk about that pi. Alright, let's begin by counting. Let's just count the even numbers up to 50. You probably know it's 25 because every other number is even. So what about multiples of 3? You probably get 16 without too many issues by dividing 50 by 3 and ignoring the remainder. And for any number really, you can just divide 50 in whichever multiple you need. To take it a step further, we can try the number of numbers that aren't a multiple of 3. Intuitively, we can subtract 16 from 50 because only those 16 are multiples of 3. Hold on though, what we did there is actually pretty useful. We took two things that are easy to count and used them to calculate something harder to count. We used multiples of 1 and 3 to find the not multiples of 3. Okay, so that may seem kind of useless from what I've given you, so let's kick it up a notch. How about numbers from 1 to 50 that are multiples of 2 or 3? It's harder, or maybe not. We can easily get the number of multiples of 2, 25, and 3, 16. But if a number is a multiple of both, it's a multiple of 6, of which there are 8. What we can do now is add the multiples of 2 and 3's, but because multiples of 6's are multiples of 2's and 3's, we would count them twice. We only want them once, so we would have to then subtract a set of multiples of 6 to make sure they're only counted once. Quickly add and subtract and we get 33. Might seem trivial still, so let's continue. How about numbers that are multiples of 2, 3, or 5, but exactly 2 of them? It's time to introduce the Venn diagram. Venn diagrams are a relic you may have forgotten about from school, but here the way it works is the number belonging to a circle belongs to the category. In this case, it's multiples of 2, 3, and 5 respectively. The intersections represent overlaps, so multiples of 2 and 3, 2 and 5, or 3 and 5. And in the center is the intersection of multiples of 2, 3, and 5. As for the use of them, I'll put the number of numbers that fall into whichever space they belong, with the exception of outside the Venn diagram, which will note any other numbers. Let's keep going. The way I like to tackle Venn diagrams is by working in to out. It's a personal display preference, and there are many ways to approach it. Anyways, I've been rambling a bit, so let's get back to math. A multiple of 2, 3, and 5 is a multiple of 30, of which there are 30. Then there are multiples of 3 and 5, multiples of 15. Doing 50 over 15 gives 3, but checking them reminds us we need to subtract the 30 and are left with 2. It's similar to what we did before, subtract out the combined case. Now we have two numbers that are multiples of 3 and 5 that aren't multiples of 2. And this should start to make sense. The Venn diagram overlap for 3 and 5 has a total of 3, but one of them is also a multiple of 2. So the rest still are in the Venn diagram, but not in the shared intersection, and thus subtracted. By the same method, we can take the multiples of 6 and 10, and just subtract the one in the middle to get 7 and 4. And now all that's left is adding the intersections that matter, which is 2 plus 4 plus 7 equals 13. Now what I did here was take a little bit of effort to go around the center intersection. Instead, if we pretended the center never existed and then subtracted it afterwards to get the same answer, we just need to add up each section and then subtract the center 3 times. This way we can get the very formulaic fractional equation that can easily substitute out other numbers. Now we can get back to pi. No, not that pi, but pi, PIE, principle of inclusion-exclusion. To summarize, we overcount what we need and then subtract it afterwards. Let's take a problem. How many numbers between 1 and 50 are multiples of 2, 3, or 5? We'll start by getting the large circles. So 50 over 2, 50 over 3, and 50 over 5 are how many in each of those. Now we overcount the multiples of 6, 10, and 15. Each of these fall into two of the categories. We only want them once, so we subtract them once. Now for the multiples of all three, they were counted 3 times by each individual, but subtracted 3 times by each pair. So it would be uncounted. So we add the last one to get 36. Although I could show you the formulas and stuff for pi, understanding the overcounting and undercounting is the most important. Knowing the formula only gets so far. Knowing the methods expands it however far you want. And this is just a challenge. If the problems here seemed simple, I'll just toss in this super extra problem I haven't solved yet. What are the odds that if you roll 8 10-sided dice, then among the rolls there are 3 consecutive numbers? Order of rolls doesn't matter, just whether the dice contain 1, 2, 3, or 2, 3, 4, etc. The numbers are pretty big, so I haven't found the calculator-ready answer yet. I have, however, used a computer to get it, so there is an answer. If you're not up for the challenge, that's also cool. I give up on this problem and revisit it on occasion, and that's something cool about problem solving. Problems that are too hard are always waiting to be solved.